All right, today we're cracking open the universe's ultimate rulebook. We're talking about the laws that govern absolutely everything, from how your morning coffee cools down to how a star burns billions of miles away. Now, I know that sounds super complicated, but the entire flow of energy everywhere really just comes down to four universal unbreakable laws. And stick with me because by the end of this, you're going to see exactly what they are and why they matter so much. Okay, so let's dive right in. The field we're exploring is called thermodynamics. At its core, it's really the science of how energy moves around and, more importantly, how it transforms. Think about how a car turns the heat from burning gas into actual, forward motion. That's thermodynamics in action. Ever stop to think about what makes an engine actually run? Or how your refrigerator magically keeps things cold? Yep, the answer to both is thermodynamics. It's this hidden powerhouse, this fundamental principle running pretty much all of our modern tech. Okay, so before we can really get into the rules, we have to define the playing field. See, in science, you can't just study everything all at once. It doesn't work. You've got to, draw an imaginary box around the one thing you want to look at. And that's exactly what we do in thermodynamics. We draw this imaginary boundary around, say, the steam inside a turbine. Everything inside that boundary is our system, and everything on the outside is the surroundings. Then we just watch how energy crosses that line, either as heat, that feeling of warmth, or as work, which is energy that actually causes movement. So this table here, it lays out the three types of systems perfectly. Think about a sealed can of soda. That's a classic closed system, right? It can get hot, it can get cold, so energy is moving in and out, but the soda itself isn't going anywhere. Then you've got a pot of boiling water. Steam is escaping, so mass is leaving, and heat is being added. Both mass and energy are crossing the boundary. That's an open system. And finally, that perfect thermos you wish you had, the one that keeps your coffee hot forever, that's what we call an isolated system. In theory, nothing, not mass, not energy, gets in or out. Okay, so once we've defined our system, we need a way to describe it, right? We do that using what we call properties. These are basically its vital signs. Things like temperature, pressure, how much space it's taking up, you get the idea. And properties, it turns out, come in two main flavors, which this slide shows off beautifully. So on one side, you've got a pot of boiling water. The temperature of the whole pot is the same as the temperature of a single drop, right? That's an intensive property. It doesn't care how much stuff you have. But on the other side, look at the scale. The total weight, the total mass absolutely depends on how many blocks are on there. That's an extensive property. It scales with the size of your system. All right, we've got our terms down, we've defined our playing field. Now it's time for the main event, the laws themselves. And we're starting with one so basic, so fundamental, that after they'd already named the first and second laws, they had to go back and create a zeroth law to come before them. Seriously. Now this might sound, kind of obvious, but this super simple rule is the entire reason thermometers work. Think about it. You stick a thermometer under your tongue. It sits there until it reaches the same temperature as your body. They're now in thermal equilibrium. And because we know the thermometer is in sync with you, we can trust that little number it shows us. It's the universe's ultimate consistency check. And that brings us to the first law. If you remember nothing else, remember this phrase, you can't win. What does that mean? It means you can't get something for nothing. Period. There is no free lunch in the universe, at least when it comes to energy. So, this law basically says the universe has a strict energy budget. It's a fixed amount, we can't create it out of thin air, and we can't destroy it. This is like reason number one why a perpetual motion machine is just a fantasy. You can't create energy to keep something going forever. All we can do is shuffle it around, changing it from one form to another. And this equation, it's like the perfect accounting sheet for that energy budget. So Q is the heat you put into a system. Think of that as your paycheck. That energy has to go somewhere, right? It can either increase the internal energy of the system, that's delta E, that's like putting cash into your savings account. Or it can be used to do work, W, which is like spending that money. See? Nothing is ever lost. It's all perfectly accounted for. Okay, let's move on to the second law, which honestly might be the most profound and mind-bending of them all. It doesn't just tell us what can happen, it tells us the direction things will happen. It's why time seems to flow forward and not backward. So if the first law says you can't win, the second law comes along and says you can't even break even. Every single time you use energy or change it from one form to another, some of it gets wasted, usually as low-grade heat. This waste increases the total disorder, or what scientists call entropy, of the universe. I mean, think about your room. It doesn't just magically clean itself, right? It naturally gets messy. You have to put in work, put in energy to create order. Well, the universe is basically one giant room that's always getting messier. This is the more, scientific way of saying you always lose a little something in the process. It's the reason why a 100% efficient engine is a total pipe dream. You can't just take heat from a fire and turn all of it into motion. You have to dump some of that energy as waste heat into a cooler place, like the air around the engine. And this is the final nail in the coffin for those perpetual motion machines. Not only can you not create energy from nothing, you can't even use the energy you do have without losing some of it along the way. And this simple three-step process you see here, this is basically the blueprint for almost every engine we've ever built. I'm talking about the engine in your car, a jet engine on a plane, a massive power plant. They all do the same thing. Take in heat from a hot source, convert some of it to useful work, and then always dump the leftover waste heat into the cooler environment. This is kind of the flip side of the second law's coin. All it's really saying is that heat naturally flows from hot things to cold things, never the other way around. I mean, have you ever seen your cold glass of water spontaneously start to boil by making the room around it colder? No way. To make heat go against its natural flow, you have to force it. You have to put in work. And that is the magic behind your refrigerator and your air conditioner, or a heat pump. They're really the same device at heart, just used differently. They both use energy, they use work, to pump heat from a cold place to a warm place. A fridge pumps heat from inside the cold box to your warmer kitchen. A heat pump does the same thing, just on a bigger scale, pulling heat from the cold air outside to warm up your house. All right, we're on the home stretch. Finally, we get to the third law. And if the second law tells us the direction of the game, the third law defines a sort of ultimate finish line, a finish line that, it turns out, is impossible to cross. So the saying goes, you can't quit the game. And what does that mean? It means you can't just stop. You can't reach a state of perfect, absolute stillness and order. That state is the coldest temperature theoretically possible in the universe, what we call absolute zero. At that temperature, all the jiggling and vibrating of atoms would just cease. Total silence on a molecular level. But the third law says, nope, you can get really, really, really close, but you can never actually get there. You can't reach that state of perfect zero. So that theoretical coldest temperature is zero on the Kelvin scale. Absolute zero. And at this point, a perfectly formed crystal would have zero entropy, a state of perfect, beautiful order. While the third law tells us we can never actually reach it, it's incredibly important because it gives us a true fundamental baseline, an absolute 0 point for entropy that lets us tie all these rules together. Okay, so let's wrap this all up in a nutshell. The zeroth law is what makes thermometers work. It defines temperature. The first law, you can't win. Energy is always conserved. The second law, you can't break even. Disorder, or entropy, is always increasing. And finally, the third law, you can't quit the game. You can never get to absolute zero, that state of perfect order. These four laws, they're not suggestions. They're unbreakable. They are the hard and fast constraints of our universe. But here's the thing. They also define our biggest challenges and our greatest opportunities. Everything from engineering a more efficient car engine to figuring out how to sustainably power our future depends on understanding these rules. So the real question for all of us is, how can we be clever, how can we innovate and engineer a better world within these absolute limits? Now that is the game we're all playing.